Okay, so we can start right now.
Yeah, good to go.
Okay. Okay, so hello everyone. Welcome to our this month's actually CASS webinar. And today we're very glad to have the Professor Jason Eshraghian to give us this talk. And Jason is currently assistant professor and a Fulbright scholar in the Department of Electrical and Computer Engineering at the University of of California, St. Cruz. And he is the developer of the Ascent Torch, very well-known Python library with over 500,000 downloads for training spiking networks. He is also a dual point IEEE CAS and EMBS distinguished lecturer, associate editor of the APL Machine Learning, the chair of the IEEE Neural Systems and Application Technical Committee, and has been the recipient of the 7 Best Paper Awards, and a scientific advisory board member for BrainChip, and leads the neuromorphic agent teams and the COSQ. Okay, so now let's welcome Jason to give us this talk.
Awesome. Thanks so much, Bo. Yeah, big turnout. A lot of familiar faces. That's awesome. Thanks for joining in. And I also want to preface this by saying, feel free to make this as I guess you can't turn your audio on, but make this as conversational as you want. There is a Q&A somewhere. I've got half of my brain looking at that, so keep it interesting, keep it interactive. I don't know, feel free to post as many memes as you want. Um, Can I tell you everything about neuromorphic computing? Absolutely not. This title is a lie because the truth is I don't know. I don't think any of us really know. Um, but we are trying to uncover the brain, or at least the parts of it that do something useful for computation. And there is a lot of uncharted territory. So yeah, every neuromorphic engineer will have opinions on how to do neuromorphic computing. And so this is honestly the best that I can do to give my own somewhat balanced view on neuromorphic computing, what it's good for, and perhaps how my lab does it. Um, so with that being said, this before we go into AI and brains and all the fancy stuff, I want to take a step back. 30 years back, right? This is me when I was 3 years old. This is my sister, Tash. And this is Tash's 2XL robot. I was too young for the 2XL. Very high tech, very dangerous stuff, major AI safety concerns. This is powered off very advanced neuromorphic tech. No, it's just a cassette. But no, so I was very excited when my sister got it. I was a little bit jealous. So my sister passed the robot to me. And yeah, maybe this was the life-defining moment where I'd go on a trajectory of working on AI. But no, I'm not here to tell you about history. This is actually a lesson about gratitude. So I was very excited. I ran off with my sister's robot, and she calls out to me, "It doesn't cost you anything to say thank you." I'm a very patient person. It took me about 30 years to prove my sister wrong because, yeah, sometime last year, April 2025, Sam Altman let us know that it actually costs you millions to say please and thank you. There's a lot of tokens, a lot of words being generated. But why is this the case? Why does it cost so damn much? Now, before we get into that, 5 years before this photo was taken, before I existed, um, this word, neuromorphic, was found in this fancy academic paper published by Carver Mead, a professor at Caltech, Neuromorphic Electronic Systems. And so what Carver says is that biological solutions are many orders of magnitude more effective than the digital computers from 1990. And to this day, I would say that still holds true in many instances. So Carver's take is that biology doesn't have some sort of abstract programming interface, rather the physical makeup of a system defines the computation itself. So he was very bullish on analog computation, using transistors in very weird ways to emulate the retina, for example, to emulate the dynamics of biological neurons. This could make a lot of sense. The physical structure of the brain dictates how the software of the brain operates as well, right? Um, but I think it's quite clear to the people in the neuromorphic crowd that the ambit of what it means to do neuromorphic computation has really broadened a lot, especially in the past decade. We're not just looking at analog anymore. Things have broadened up a bit. So rather than giving you my own formal definition, I will try to offer you some intuition instead. How do I personally interpret neuromorphic computing? I kind of see it as the opposite of biomedical engineering, right? Biomedical engineering is all about taking circuits or algorithms or something, some process, some technology to modulate biology or some biological process. You kind of put it in, right? Neuromorphic computing goes the other way, where we're taking inspiration out in order to make that technology, the algorithms, the chips, etc., a little bit more effective. And so yeah, the key word there is really inspiration. We're not necessarily control C, control Ving the brain. I don't think that we know enough about the brain to make that productive, but rather just taking the parts of it that we care about. So given our limited understanding of the brain, what can be leveraged? Let me offer you three S's of some things that are valuable in the brain. This is not exhaustive. There are many other things that are useful in the brain, and you could argue that some of these S's are kind of useless at times as well. But let me break it down for you. So one is that biological neurons interact via single bit spikes. If I take this electrode and let's say for a moment I move the electrode, I stick it into the neuron body, then this scope will show me a bunch of noise, right? I mean, it'll be showing something perhaps meaningful, just hard to interpret. But then if I move that electrode just like 1 to 2 millimeters away from the neuron body, down the axon, a lot of those voltage fluctuations would just kind of go silent, right? They'd go silent until the neuron was sufficiently excited and it triggered its own spike or action potential, right? And that's just a voltage burst of approximately 100 millivolts in magnitude that goes up and down. And a lot of computational neuroscientists are doing studies at the population level. So some folk will say that it's commonly accepted that most action potentials look very similar in terms of amplitude and pulse width and whatnot. And so maybe it makes more sense to take a step back and represent action potentials as just a stream of ones and zeros. If you have a spike, if you have an action potential, 1. If you don't, 0. In terms of computation, it feels not too unproductive because maybe we need to put information, we need to encode information over time instead of in the amplitude. And we're quite comfortable that the brain does some sort of temporal processing. If I was to take an artificial neuron and just replace it with a biological neuron that is doing this abstract mode of spiking, then maybe that also makes sense because every time there is a 0, that means I can effectively skip an operation, right? If a neuron is broadcasting nothing out, if it's broadcasting a 0, then that's a memory access step that I can skip. And we hopefully can appreciate that most, not all, but most processes in the deep learning world tend to be memory bound or memory limited. So we're only accessing memory. We're only doing computation on data in memory when there is something salient, which leads to this idea of sparsity, right? And biological neurons are ridiculously slow compared to CPUs. They're pretty damn slow when it comes to spiking. So most of them can be thought to be at rest at any given time. They're not at gigahertz frequencies, right? They're spiking once or so per second. It's on the order of 1 hertz. If I give you this list, I could read it out and say 0, 0, 0, blah, 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 7, 0, 0, blah, 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 5. That was a waste of everyone's time, right? That's a very inefficient way to express this list. So it may make a little bit more sense for me to say there's a 7 at position 10 and a 5 at position 20. That way, I'm only adding to my memory usage every time there's a non-zero element. So this can help with caching activations that are sparse as well. So these two are very related. They're both piggybacking off some type of sparsity. But this first S is all about reducing memory access, whereas the second S is all about using memory a little bit more effectively and compressing information in a more intelligent way. The final S looks more at the sensory periphery rather than the computation. And so the sensory periphery only likes to process information when there is something new to process. Rather than showing you static images, let's see if I have an animation of sorts, right? This is some footage taken from my buddy Greg Cohen, professor at Western Sydney University. So on the left, you're seeing a construction site in Western Sydney. I think I'll be there in like 48 or 72 hours or something, with a conventional camera at 30 frames per second. On the right, you have an event-based camera that only reacts to luminance changes. That's cool. You might be able to isolate a little bit of rain. These are moving pieces of the image that are not so clear on the frame-based camera. So, you're able to extract something interesting. But what is perhaps even more impressive is that the fact that you're suppressing so much of your scene is static, right? You can kind of take that suppression of information processing and allocate it to something else. And what does that look like? Well, if I'm not processing things spatially as much, then maybe I could increase my temporal granularity. And so it turns out that you've got commercial event cameras out there being manufactured by innovation, by prophecy, and these are operating on the order of tens of millions of events per second, at a very, very constrained power budget, right? If I go into Hollywood to get a high-speed camera that can capture not even a million frames per second, those cameras themselves will cost me hundreds of thousands of dollars to purchase or to rent. Event cameras, not so bad, right? You can get a little plug into an STM32 for something like 500, $600, which is quite amazing. That's sensing. Sensing is important. Spent a fair bit of my PhD focusing on that problem, but as I grew older and lost hair, I would argue that our demands for efficient computation are somewhat exceeding our demands for efficient sensing when it comes to most deep learning workloads that are commoditized now, like language models, etc. How can we actually do computation with biological neurons? I swear, I'll stop the cute slides in a moment. We'll get into the technical meat of it. But the story goes back to 1907. It starts with this little guy. So Louis Lepic, he was a French neuroscientist, and I don't know, before he ate his dinner, he stuck a set of current probes into a frog's leg. He measured the time it took for the frog leg to twitch, and he found a relationship between the strength of the current and the time to twitching, and it followed this kind of exponential relaxation process. So yeah, this is definitely one of my most questionable slides. All of this is to say that it led Louis to a mathematical formulation of these relationships as a first-order dynamical system. Some of you know where I'm going with this. One of the most famous neuron models is the leaky, integrate, and fire neuron. Without understanding the physical mechanisms underpinning this neuron, Lepic was able to model it pretty damn effectively. He found cases where there was no twitching. He found that if the leg was sufficiently excited, it would twitch. He inferred that to mean that there was a neuron or a population of neurons that are also spiking in response. So the vibe is something like this, right? Take this neuronal abstraction. If this neuron is sufficiently excited by these incoming spikes that vary over time, then that neuron transmits its spike to all downstream neurons. And it looks something like this. If I probe the difference between your intra and extracellular medium in response to this input current spike, then what we see is this membrane potential. It jumps up and it exponentially relaxes back to a steady state value, which is all normalized on the y-axis. That could be thought of as some sort of short-term memory, right? This is sustaining the response from the input current. That can be thought of as our leak, right? Charges leaking over time. What about our integrate? Well, when you have a bunch of spikes, then these membrane potential trajectories are sort of riding on top of themselves, and so that's our integration, right? How about our fire? If I set some arbitrary threshold, mind you, this threshold is dynamic. This is a far more complex system than what I'm making it out to be. But if the membrane potential hits the threshold, then that's when you transmit your one. That's when you run your memory access and so on. So we took that guy, scaled it up. This was my pandemic baby. I developed SNN-Torch, which is just a thin abstraction layer on top of PyTorch to make training spiking neural nets far easier. And there is a deep story as to why I built this. And it actually all goes back to work on in-memory computing and trying to find algorithms that are far more robust for noisy memoristic devices. But I'm not going to go there today. But enables you to pull all your gradient-based techniques that the deep learning people have come up with and applying them to spiking neural nets. There's a few interesting learning rules out there. If you know how to use PyTorch, SNN-Torch is really mind-numbingly easy. It's had a couple of downloads. I think I have to update that number. And it's also compatible with neuromorphic hardware since the neuromorphic intermediate representation came out, and a few places are using it. NASA in particular is a cool one. Some of their research arms have let me know that they've played with it. And it makes sense, right? If you're pointing a camera into space, what's in space? A lot of nothing, right? So you don't want to be processing a lot of nothing. I want to be a little bit more efficient about it. And I've also written a painful amount of tutorials that are, I kind of consider this a sort of dynamic and interactive textbook. So yeah, if you want to get deeper into the details, where these models come from in a mathematical and coding sense, this is a great place to start. With all that being said, it's not surprising that language modeling is one of the places where I'm exploring the utility of neuromorphic computing. There is, of course, the energy efficiency angle, but I don't know. I think some people view language as like the foundational unit of logic and reasoning. And while that could be a separate debate, doesn't it make sense to use brain-inspired concepts to do brain-like reasoning? So let's take a look at a snapshot of some of the things that we've done. But to motivate why we want to avoid using modern transformers and modern language models the way that we currently are, let me give you this silly sentence. Shrek saw Taylor with binoculars. My question to you is, who has the binoculars? Is it Shrek? Is it Taylor? Now, linguistically speaking, it's ambiguous. We don't know if binoculars is tied to Taylor or if Shrek saw somebody else and he was holding the binoculars. Intuitively, in some basic deduction, we know that Shrek saw somebody else, therefore he's more likely to have the binoculars, right? Why am I explaining this? Well, give me a moment. When I pass this into a language model, each of these words, more generally, tokens, are going to be fed as a vector. These words are going to be represented as numbers. They're going to be fed into a language model one at a time. And then you're going to process on them, and eventually somewhere in the language model, in the transformer architecture, you're going to generate what's known as a self-attention matrix. The self-attention matrix is effectively looking for correlations between the tokens, between the words of your data set. So in this example, you should hopefully be able to appreciate that if I add an extra word, I'll get another x dimension, another y dimension, right? And another element in my x, another element in my y. So this matrix just keeps growing. So I'm going to use, with a very naive implementation, I'm going to have quadratically scaling memory. But the point is, I'm storing every word. I'm storing more than every word, right? Storing every word squared, yeah? So the memory should be kind of perfect, right? My language model sees, yeah, there's a tight link between Shrek and binoculars. Maybe there's a link between Taylor and binoculars, but it's not lit up as much, right? The thing is that memory is growing quadratically with your sequence length. And I think as I'm talking to you, you're not storing every single word in the right sequence. Hopefully you're just taking the meanings of what I'm trying to get at, and I don't know, something clicks, maybe you come up with your own analogies, but you're not storing everything I say perfectly, right? So your brains are not undergoing neurogenesis with every word I say. So the catch here is that if I was to apply this to a recurrent neural network or a spiking neuron, the risk there is now that, by the time that I reach the end of my sentence, there is this risk that all of that information is kind of decayed, right? I'm not expanding the state. I'm not adding extra states, but I'm using the one variable to represent all of my history. And the problem with that in spiking neural nets and recurrent neural nets is that you get fading memory. And it might be the case that all my information about Taylor supersedes and overwrites everything about Shrek in my model. Now, of course, this is a very toy example, but I hope you can see that maybe this input current represents Shrek somehow, and then my membrane potential jumps, but then by the time I reach binoculars, everything about Shrek is gone, right? So there's this short-term memory problem that actually is one of the major reasons why people abandoned RNNs for language modeling and went over to transformers. So we're really trying to bring that back. We're trying to say that attention has too much information, but damn, it works really well. Spiking neural nets, and more generally, recurrent neural nets, seem to not have enough information, but they can be really cheap. How can we bridge this gap? So in, 2022, one of my earliest PhD students, Ridger, he started working on language modeling with spiking neural nets. he came out with Spike GPT, and I'm not going to go through the low-level details of this architecture, but it was the largest SNN trained via backprop and the first to successfully perform language generation at the time. And the headline catchphrase was, yeah, 30x less operations than a transformer of equal size. But if it's all that well and good, then why aren't people using it, right? Scaling hurts. It's an open source model. You can download it. We uploaded a 216 million parameter model, which is very big by SNN standards, but it's also 10,000 times smaller than modern trillion parameter language models. So it's a toy. I consider it quite a toy now. And we were very transparent in the Spike GPT paper as well. We trained a 1 billion parameter version of it, and the performance did not follow the scaling law trajectories. We did not do as well as what we would have hoped. So I was kind of left thinking, did I just waste all my years working on spiking neural nets? Am I using them wrong? What's wrong with me? I got very insecure. No, I didn't. But we figured that recurrence is critical, but perhaps we're not able to figure out the compression of information very effectively. I think a lot of spiking neural net papers start off with the non-differentiability of spikes is a big problem. Honestly, I don't think that's a major problem anymore, right? I think people have come to realize that gradient approximations and surrogate gradients and smoothing out derivatives is perfectly fine, provided it's done right. We've seen that in quantization-aware training, right? Gradient approximations work very well. Your model is very robust, especially as it gets larger and larger. So really, I think what the problem with Spike GPT and many other spiking models is that you're just compressing your activations too much. I say that because every spike is a 0 or a 1, it's all about when the spike occurs. But I don't think we've done a good job of figuring out how to take advantage of that. And I say that is still an open question at the moment, and I think that we could do better there. But what we did do, we took a lot of the learnings from Spike GPT, and we developed this other model, matmul-free. And so this has been it's still ongoing, right? We released the initial preprint mid-2024. We released the hardware implementation on Loihi on neuromorphic hardware approximately 8 months ago. And so we've updated the preprint with all of those results. But matmul-free is a recurrent model. Instead of using binary activations, we're instead porting all of the learnings from low precision models into ternary weights, right? And matmul-free, it is the first billion parameter scale matrix multiply free model to achieve language generation. It uses ternary parameters, so 8 to 10x less memory than your 16-bit brain flow precision models. And because you're doing a recurrent process, you're not expanding memory here. So this looks a lot more like a spiking network than it does a transformer. But if you're trying to compress a whole heap of sequence length into a single state, you need to learn how to forget. And so we drew upon a lot of the pre-existing literature from, say, LSTMs and forget gates in order to implement this guy. We ran this on neuromorphic hardware. Our initial implementation was at 13 watts, but thanks to some geniuses at Intel, Sumit and Steve at Brew, that we were able to get this squashed right down to 2 watts with billion parameter scales, which is quite cool. So we are relying on GPUs to train these models, but GPUs are not very effective at milking ternary operations, right? So we look at custom hardware, and I don't know, we wanted to meet the NeurIPS deadline. We had 3 weeks to make this happen. So let me step you through what the results look like. On the x-axis, I have sequence length. On the y-axis, I have throughput, the number of tokens generated per second. Higher is better. Most of these colors are all a regular transformer model. So transformer plus is kind of a very representative model of, say, Llama and most open source LLMs that are out there. In blue is matmul-free, and I say all sizes because we just sort of changed the number of cores used to normalize everything. And what we're seeing isn't that great, to be honest, right? As the sequence length goes up, then sure, then that's when the quadratic scaling hurts transformers. But the short sequence length regime, this doesn't seem too impressive. You could argue on my behalf and say, yeah, but models are at 128,000 sequence lengths, so that you're going to definitely win that. But the one thing that I haven't really captured in this figure is energy, right? And so energy is what matters. This is a high-level view of the sequence of steps in the software. This is all, of course, optimally mapped to Loihi. And there's two phases with language models. There's pre-fill. And pre-fill you can think of as, you're typing in a chat GPT, you've built out a full sequence length, and then you hit enter to predict the next word. That is, so pre-fill takes a full input to predict the next token. Autoregression has now generated that next token. And what decoding or autoregression is trying to do is still predict the next token, but I only have one new token to work with. So every language model sort of works like this. It starts in the pre-fill phase, where it's operating on many tokens, and that's very compute heavy. Once that's done, and it's only doing one token at a time, that's decoding. That is memory bound, right? Typically, compute is underutilized in that case. So we had to account for both of these situations. With autoregression, you're kind of, I should mention, map-more-free doesn't take advantage of sparsity in the way that I've presented it to you. But autoregression naturally gives you free sparsity because your pipeline isn't full. All of these other chips are basically off, right? Loihi is an asynchronous chip, so being event-driven, the only energy that's being dissipated is really to keep the SRAM alive in static power, which is actually very expensive. But there's other things to be said about that. So we deployed this on a set of Loihi 2 chips. I believe the 1.3 billion parameter model, we squashed that down to something like, I want to say between 8 to 10 Loihi chips. I say 8 to 10 because we're constantly doing better. We inject a bit of weight sparsity and we can compress it down further. We want to capture energy, right? X-axis is joules per token. Joules, lower is better, right? So we want to sit here. On the y-axis, we have throughput per watt. How many words can I generate per second given 1 watt of power? Higher is better. So in this picture, I want to sit somewhere here. So forgive me for having such a VC-friendly pitch deck animation, but what you're seeing here now is Transformer++. This is what we're trying to beat. This is the 1.3 billion parameter model and the 2.7 billion parameter model. If I zoom out considerably, then I can see where the map-more-free model sits. And it's exactly where I want it to be. That's all well and good, but keep in mind, these are ternary models. The Transformer++ models are going to be BrainFloat 16 models. And so if I normalize the size of these circles to the amount of memory they use instead of the number of parameters, we're doing far better with a lot less. In terms of benchmark results, for almost everything that cares about short context windows, we're more or less on par. So ternary models are really quite robust. When it comes to long context benchmarks, that's where recurrence starts to break down a little bit. So needle in a haystack type tasks, recurrence is not so effective at those. But people have been able to use hybridized models where, say, 80% of your model is going to be recurrent, 20% of it is a transformer, and that lifts up your long context modeling as well. So can we use efficiency to reach state of the art, right? That was the next question that we asked. What I'm showing you is very much in the spirit of we're doing really well given a very constrained budget. But logically, shouldn't you be able to apply these efficiency gains to much more compute intensive models to let your top end models do better, right? Shouldn't you be able to breach past that ceiling? That's the next question that we asked, right? With Spike GPT and map-more-free, those are trained on, say, like map-more-free is on about 100 billion tokens, which isn't very much compared to large-scale models, right? Those are in the trillions of tokens scales. So this is where we're trying to kind of go a little bit more crazy. And so to express that, I need to run you through the projections and scaling trajectories of models, right? So this comes from Kaplan's work from OpenAI back in 2020. Really, I'm going to distill these findings in a very simplistic way, right? As your model size gets larger, your test loss goes down. Okay, that's obvious, right? They found curves to fit that. As your data set size goes up, test loss goes down as well. Okay, cool, right? But what they really found was something a little bit more interesting, and that's that, as your data set increases, your compute increases. As your model size increases, your compute increases. So they were really focused on finding what's the Pareto optimal frontier. Given a particular amount of compute budget, what should my data set size be? What should be my model size as well? So, all these curves represent various training runs, and they found your compute optimal frontier along this line. Okay, that's fine. my question to you now is, what is the limiting factor of these three things? Is it data set, the model sizes, or the amount of compute that's limiting scaling language models, right? Because we are seeing a bit of a saturation in performance. I think that is fair to say. Now, the answer is actually the data set, right? We've effectively exhausted much of the high quality internet, and the high quality internet is not increasing at the same rate as the amount of tokens that our models are ingesting. So what can we do on that about that? If we have an upper bound on data set, then it means I could throw more GPUs, I could throw more power, I could do in-memory computing, I could do all these fancy tricks to improve my model's training runs, but it's effectively useless for the large-scale regime if I'm data bound, right? My question now is there a way to decouple these things? Can I decouple my data set from my compute? Reasoning models are a logical answer there, and we've already seen reasoning models being deployed, right? Where the way they think over time, these models are talking to themselves. We've seen that in ChatGPT and Gemini. We've seen this in Claude, all your favorite grant writers. What is a reasoning model? I mean, the most simplistic way of expressing what a reasoning model might be like this, right? I ask it a math question, and it goes ahead and breaks down a set of possible candidate answers, and maybe then, bam, one of those is correct. The model gets a reward for that one correct answer. Reasoning is more general than this, right? Maybe getting each of these answers took a sequence of, 6 plus 6 plus 6 plus 6 plus 6 divided by 2. So breaking things down is a reasoning model, right? You could simply tell the model think for a longer time, and that is technically a chain of thought. So one of these answers is correct, and it breaks this equation down into smaller subpieces. So effectively, you're getting a more probable answer by extending the chain of thought. The problems with these reasoning models is, one, it extends your context. You're using more of your memory to generate the final answer, right? Two, your pre-trained model still needs at least one correct answer. So if I want to reward a reasoning model, then one of these needs to be correct. So the way that ChatGPT and all these models are trained is like this. You have a base model, right? You have a pre-trained model, and then we reward it after the fact for reasoning effectively, for generating good code, for succeeding in math competitions and whatnot. But it relies on a pre-trained model. And so the thought here is that if I'm going to get a successful post-training RL run, my base model needs to at least be able to get that answer correct once for a reward. In absence of that one correct answer, then it's not much that you can do there. What can we do to increase the chances of getting that correct answer? Increase your model size or your data set size. That's a bit of a catch-22, right? Because I'm trying to decouple data set size from my overall compute. And finally, it operates on your vocabulary. Why is that a problem, right? Like you're kind of taking these variables and looping them back in. But let me give you a cute example. So in Iranian culture, my parents from Iran, but there is this kind of polite ritual of give and take. I go to my auntie's house and she'll offer me tea and desserts and cakes, and I will always say no. I'll say no, it's okay. Don't trouble yourself. I would decline at least 20 times, but she's going to keep persisting. And so this polite give and take is honestly a bit of a ritual amongst Iranians. It's so ingrained in our culture that it has a word, off, right? There is no equivalent word for it in English. What that means is that doing reasoning on the outputs of this text cannot be the most optimal way, especially when there aren't a sufficient number of words to express these kind of niche or culturally specific sorts of contexts. So chain of thought rollouts can be thought of as just recurrence, right? You're feeding in the output text and you're computing on that output text rather than some vague latent space embedding. So we effectively went ahead and tried to fix all of these things in one hit. We recently released this model called Scaling Latent Reasoning via Looped Language Models. There's a few open source models that we've released, 1.4 and 2.6 billion parameter available on Hugging Face with thinking versions. How does it work? What's the deal? On the face of it, I can express this very simply, I think. You take your input token, pass it through your model, just as per usual. A regular transformer will then go to the next token. But what we do before we unembed this latent vector into a word, into a token, we pass it through an exit gate that says, am I happy with that? Or should I try again? Right? If it's happy, then yeah, you go through the head and you go to the next token. But if the exit gate says, hold up, I'm not confident about your answer, then it's going to loop that back around until the exit gate is satisfied with the output result. And so I would say that this is effectively a third scaling dimension for pre-training, because this can be done at pre-training. This isn't like a post hoc, post pre-trained model process that all the current big tech companies are working with. Your data loops through the model, and there's this dynamic termination process, simple versus hard. If you have a simple token, then you could expect less looping. If you have a hard token or hard variables that need to be predicted, then you're probably going to compute on it a little bit more. And this is all operating on the latent space as well. It is the first looped model to be trained at an industrial scale. So, with Spike GPT and Matmore-free, those were pretty GPU constrained. Those were maybe, I don't know, a few days of running A100s. This was closer to a couple of months, right? With a lot of errors in the pipeline that had us redoing and recleaning things up. So 7.7 trillion tokens, that's a really serious scale that exceeds millions of dollars of training runs. But yeah, it was kind of nice because it was a case of demonstrating that we were able to do something pretty decent with a very constrained amount of resources with Matmore-free. And so, then we were able to get a bit of a more sizable investment thanks to ByteDance and several other companies. And this is a radar plot that effectively shows you the performance. At a high level, it's effectively doing just as well on most benchmarks. And we're comparing the 2.6 billion parameter model against the state-of-the-art small language models out there. So, Gemma 3 from Google, 4 billion. QN3, 4 billion. QN is from Alibaba and really state-of-the-art in the small language model space. But we're also comparing it against 12 billion and 8 billion parameter versions, right? And keep in mind, QN3 is trained on like 20 trillion tokens, right? So I would argue that even though there may be a little gap on one of these benchmarks, this red radar is doing pretty damn well. So I feel like this really goes from language models that are academic in nature into things that are actually competing with what industry are generating. I'm not going to go through this, but I just want you to be aware that we do have the entire training pipeline all written there, like in a technical report style in the paper. And I think this is really interesting stuff. It even goes through the distribution of data and how we evolve that during the training run. But the point is that recurrent transformers are effectively enabling 2 billion parameter models to perform at the level of frontier 8 to 12 billion parameter models. And I think that that's really quite remarkable, right? And on top of that, there are a lot of opportunities in leveraging looped models on a hardware front, on a circuits and systems front, right? Because we haven't seen weight reuse in a while, right? Convolutions came about, and you're suddenly compute bound because there's so many operations that you can run. You can get a highly optimized convolutional kernel to parallelize all your cons because you're reusing your kernels so frequently. Language models kind of broke away from that. Language models went back to a lot of dense layers, a lot of dense operations. But now there is this opportunity for leveraging weight reuse again, thanks to your looping, right? So yeah, a lot of open questions there. The thing is that targeting the language model space is honestly a little bit of a weird one for the neuromorphic world, right? I mean, my lab is very focused on high-powered applications, and while a lot of that can be taken to the edge, I would say that if you're able to improve the operational costs of a huge server environment, then a 1% improvement comes with a huge amount of reward. But most groups are indeed looking into finding lightweight applications for neuromorphic computing. And this is perhaps equally useful because there's certain applications which just do not have the power budget that language models have access to. And so perhaps neuromorphic computing is the solution to enabling some of these more resource-constrained technologies. So I'm going to go a little bit meta here, right? I'll show you some of the questions we've been asking on how can we use brain-inspired principles to perhaps help the brain. And I'll give you a rapid snapshot of some of the cool things that might fall a little bit more squarely within the biomedical circuits realm. But this is my final story for you before I go back to tech. So when UC Santa Cruz made the mistake of hiring me, I caught the bus. The American DMV did not recognize my Australian driver's license, and so yeah, I take the bus to work. This is my view from like 5 minutes away from my office, so it's quite stunning. And I was sitting by the window. I was like, "Oh my God, shit! This is amazing, right? This is incredible." That's day one. Day two, still amazing, right? Now, how long have I been there? I think I'm in my third or fourth year of working at UC Santa Cruz, and now it's like, God damn, I've got to grade 100 papers, I've got to deal with 3 million emails, and I stopped paying attention to what's outside my window, right? Part of that is because it's not just because I'm complaining about my job, but it's because you get used to it, right? You get used to what's outside of that window. The point is that the brain will suppress information that doesn't necessarily surprise it anymore. And this is very tightly related to this idea of predictive coding. Right? Your brain really learns from surprise so that you cease to be surprised again in the future. You get a little desensitized to your sensory experiences. Is that a good or bad thing? I don't want to go philosophical, but let me tell you how we made this scientific. Let me tell you how we took advantage of this idea. I'm going to use a seizure forecasting as my canonical example. The setup is this. Take a bunch of electrodes, multi-channel EEG setup. You're extracting electrical signals from the brain, and what my goal is here is to pass that signal into two models. Model one is trying to detect seizures. It's trying to say, is there a seizure right now? The other model has a harder job. It's trying to tell me, will there be a seizure in the future, 30 minutes into the future? So I hope you can appreciate detection is easier and forecasting is not so easy. But forecasting is really useful because if you can tell something in advance, it's going to enable preventative measures, right? But it's difficult. Whereas with detection, you could argue that, as far as time horizons go, it's as good as it gets. So we recently published this new learning technique, future-guided learning, in Nature Comms. My undergraduate student started working on this. She started working on this in her second year of her undergrad, and then recently got it into Nature Comms, which is pretty awesome. Here's the setup. We start moving in time, and eventually the detection model says, "Ding, ding, ding, there's a seizure." But the problem with this picture is this: the forecasting model 30 minutes ago should have been able to predict that seizure. So if there is a mismatch between these two models, then we can use the detection label to update the forecasting model. And we just keep doing this over time. It's sort of like a continual learning problem now. And we're using the future to help guide a model that kind of sits in the relative past. So that's all well and good. There are a few catches here because the detection model may get things wrong as well, right? The detection model is not guaranteed to be correct, but the thing is that as long as the forecasting model does as well as the detection model, we're happy because now we're treating the detection as our golden standard in a way. It also means that other than pre-training your detection model, there is no need for manual labels. You don't need an expensive neurologist to hand tick all of the seizures on an EEG reading. As a result, it does open the opportunity up for patient-specific forecasting because you're going to attribute a forecasting model to an individual patient, and as a result, we were able to get higher performance metrics across all the data sets that we tested across various tasks, not just EEGs. Let me average out these data sets for you, CHB MIT and American Epilepsy Seizure Society. The AUC ROC, just if you're not familiar with the area under the operating characteristic curve, just think of it as like an alternative metric for accuracy in very imbalanced data sets. In green is future-guided learning, blue and red were the prior SOTA methods for seizure forecasting, and we're quite comfortably doing better than what was the state of the art before that. But it's worth mentioning that this future-guided learning can be wrapped around whatever model you want. So it's not like these things are orthogonal to one another whatsoever, right? The takeaway here is that you can minimize surprise by learning from the future. I think that's kind of cool. How's the training cost? You're only learning at mismatch. That's good. That can be relaxed, right? You could have a perfectly matching seizure, but the logits might be slightly different, and you could keep training and if you really wanted to. But a problem here is that you're now relying on multiple model deployment. That's more expensive. How can we make that cheaper? I, I ask, could spiking neural nets be the right solution here? Intentionally with a question mark. But I want you to think critically here. Does that address the right problem? Let me be brief about this. If I was to do any sort of neurostimulation, let me break it up into sensing, controlling, and the final act of the stimulus, the neurostimulator. In the case of a seizure, let me denote this with medium and low power drain. And low to medium is a 10x, and then low to high is another 10x. So we're going from tens of microwatts to single digit milliwatts. Sensing can be medium to low. Controlling can be very low if we're offloading the work to sensing. And then neurostimulator is going to perhaps have medium drain on your power on your battery. Epilepsy, it's a very bursty workload though. You're not always stimulating. So there will be regions of very high power draw, and then otherwise it'll be largely quiet. This is very different from a situation such as addressing Parkinson's disease, where it's a far more continuous situation. Your stimulus is more continually going to be on. What I want you to really pay attention to here, though, is which of these three requires a neural net? You don't require it, but which of these three could benefit from a neural net? Well, the sensing that says, yeah, there's a seizure or no, there's a seizure, that could benefit from a neural net. You could have a neural net in your controller that says, given what I've sensed, should I activate the neurostimulator? But the neurostimulator itself, that's kind of on its own. That's just drawing power to zap the brain, right? The point is that the highest power drain sits in the neurostimulator side. Everywhere that there isn't a neural net. So if I add a spiking neural network, am I addressing the right problem? Right? This is what I think a lot of academic groups do struggle with that a little bit, right? You don't want to be enhancing the efficiency, enhancing the sparsity of 5% of your total system budget. It doesn't necessarily make sense. And so and I've been guilty of that for a lot of my research career, but we started working on this final learning rule that I want to bring up, and this is energy aware learning. And I like it because it feels neuromorphic in the sense that the brain is optimized for the amount of resources that it biologically has available to it. It's optimized for the energy that it can afford to expend. And so we're kind of taking inspiration from that. Here's the setup. Take a rat model, extract neural data from it, throw that into a Parkinson's disease classifier. Of course, the rat is inflicted with PD. Say you deploy your SNN onto neuromorphic hardware and you apply that to a controller that says, yes, let's stimulate, no, let's not stimulate. This is vanilla, right? The obvious thing to do is reward for how well you suppressed Parkinsonian behavior. That doesn't address the right problem though. So the second loop to add here is your energy and latency. We reward the system for activating the neurostimulator on a stringent budget. In this case, that's energy. We reward it, we allow frequency, pulse width, duty cycle, all these kinds of variables and amplitude, of course, these variables that define the neurostimulator control setup, those are treated as free parameters, and we combine the efficacy and the energy of the total system. So you reward your model for total energy usage in addition to working effectively. That's really how to go beyond just addressing 5% of your system and addressing the full system itself. In practice, you combine the sensing and control neural nets, and we tested out a bunch of things. This is just a snapshot of one reinforcement learning trajectory where we want the alpha beta power to fall below this red line, which it is a model. We're assuming that anything below this line is suppressing, I guess, neuronal firing or the power to a point where you are able to address Parkinson's disease. And of course, this is going to be different for different humans. And this bottom plot just shows you how the frequency and amplitude and pulse width were changing. At the start, it's very exploratory. The system is testing out different options, and then eventually it settles. We did sweep across sparsity, and we ran this on Xylo. So as we go from left to right, we're testing out 10% sparsity, 5% sparsity, and I guess in dark blue, you have latency, and in lighter blue, teal, you have the SNN core dynamic power. And right, you're at the microwatt regime, which is awesome, right? But if your neurostimulator is going to be several watts anyway, milliwatts anyway, then we kind of found that sparsity didn't matter so much in this particular use case. the fact that you're using an asynchronous SNN with an asynchronous accelerator was enough. So you don't need to reward sparsity, because the benefit is just going to be too incremental in that situation. So with that being said, I hope that I was able to shed some light on this trajectory of what research we've done. None of this is possible without the honestly absolute stars in the lab. In particular, where is he? So Ridger, where is Ridger? There he is. Ridger's the guy that led a lot of the language modeling work. Sky back here led energy aware learning. Sorry, Sky led future guided learning. And whereas Bin over here, he led the energy aware learning project. So with that being said, here's a set of references that may or may not be useful. Feel free to screenshot that or go back to a, I don't know, recording of this video and screenshot it. And I'm happy to take questions. Excellent. I think I can probably self-assemble the Q&A. So
Yeah, there's several questions in the Q&A. Yeah.
excellent. Okay, so Giovanni's got several questions here. Is SNN torch a neuromorphic intermediate representation? No. It is a thin abstraction layer on top of PyTorch. It outputs models that are expressed in the native PyTorch.pt's type format. There is a separate library that was led by Jens Petersen, and we worked on it together in a largish consortium across academia and industry to develop this separate library, literally called Neuromorphic Intermediate Representation, which takes various library models. So SNN Torch is one example, Spiking Jelly, Lava from Intel, all these different spiking neural net libraries that express dynamical systems in discrete time. And the output is going to be a common standard that lets you transfer that into any other of the same formats. So not, yeah, I think that clarifies that. And the next question, what are my recommendations for improving the Pareto optimal frontier for neuromorphic processes? Use in-memory computing, an RM or analog neuromorphic, or hyperdimensional computing, or optical computing, or quantum computing. I don't know. I would say I don't really have a good answer for that. I think it's really a case of use the right tool for the right job. I mean, am I going to run a neural net to neurostimulate myself using quantum computing? Absolutely not. I don't want a massive refrigerator carried around with me to suppress the behaviors that I don't want. I mean, neuromorphic computing might make sense when you have a ridiculously low budget, but what is neuromorphic computing? Some folk interpret it as in-memory compute. Some folk interpret it as sparsified and recurrent compute. In the case of recurrent compute, if your data set's going to be time series and time varying, then yeah, it starts to make a fair bit of sense. If your data set is very tolerant to noise and the non-idealities that memristive and RAM variants come with, then that could make sense as well. But yeah, there is no one clear-cut answer. It's really just a kind of decision tree of what makes sense to the right technology. Let's keep going. We're deep. So I'll go to some other questions, then come back to Giovanni's. Can I tell you something about Spike GPT? It's a recurrent state space model, and there are YouTube videos about it if you want to go into more detail. Epiphanios, to what extent do I consider biological plausibility an important factor when I create SNNs for engineering applications? I'm going to treat that as a very personal question. Biological plausibility is secondary or fucking tertiary to me. I am thinking engineering first. Sparsity, for example, can make sense in some cases. It doesn't make sense in all cases, though. So I'm always thinking about the engineering of it. Otherwise, I'm probably not going to pay a huge amount of attention to. I think some of my research has been criticized actually for not taking enough inspiration from biology, but my goals are different. My goals are honestly to have something that can translate a little bit more readily into things that are, I guess, immediately industrializable or within a 3-year time horizon. But that's just me, right? Many other folk researchers have the freedom to explore on longer time horizons, and I don't think it's a bad idea to do that either. What are the advantages of sensor data processing with SNNs? I think the 3S's captured that pretty effectively. You're reducing data transmission. You're potentially improving the amount of memory utilization as well. That's going to be cost and latency. What do I think of FPGA-based SNN accelerators? Yeah, so I'm a little bit skeptical, just largely because FPGAs for the most part are all synchronous, and SNN benefits really sit in asynchronous processing. Um, so it's a difficult abstraction layer to program to write FPGA accelerators for SNNs. That's not to say they're useless by any means. I think that they're a fantastic tool for education. They're a fantastic way to perhaps get some uh, uh, um, basic proof of concepts for the work that you're doing. Though I don't, they're of course not the optimal mode of implementing SNNs. Um, yeah, thanks for the kind words for us. Oh, Alp, good to see you. Familiar name. Could we split a large language model into core layers and task-specific layers and run them centrally and at the edge, respectively? Yeah, there is a lot of work on distributed processing out there. We have a bunch of mobiles, each with little sub-pieces of networks, and they're talking to each other. Yeah, the LLM research space is just painfully fast, right? What you're describing has been done. Maybe not to a super mature point, but yeah, a lot of smart people working on LLMs out there that I can barely keep up with. Um, how do I see the neuromorphic sensors regarding its precision? I'm not sure I fully understand the question, so maybe I'll come back to it if we have time at the end. You want to know about neuromorphic computing related to power electronics? That'd be cool. Um, and Varick asks, what do you think the gap or the next steps for the implementation of the epilepsy models are? Yeah, I mean, a few different forks here. I mean, of course, generalizing to larger data sets, trying to test this actually in a real world setup with real people with uh, prospective data rather than retroactive data or retrospective data, which is what we did. Um, those are probably the best things that we could do. I also love the idea of applying continual learning tricks to this tech to future guided learning because it is effectively a continual learning problem. We didn't do anything continual other than the learning setup. So I think that'd be kind of cool if anyone wants to work on that and then add me as 215th author. I'm just kidding. You don't need to do that. Um, how much research is currently being done on neuromorphic hardware? Loads. ETH Zurich, INI are a fantastic, is a fantastic institution for a lot of that. TU Delft, Charlotte, she's crushing it. She's doing awesome work. There's a lot of cool work in China as well. There's loads. I can't keep up with it. It's great. Can we use SNNs for feature extraction? I would argue everything in here that uses an SNN is implicitly feature extracting. What about optical neuromorphic chips? I don't know much about optical neuromorphic chips. I think the device community know more about that, but intuitively makes sense because a lot of optics do rely on latency and rely on timing of packets of light. And neuromorphic is timing based, and optics are often yes or no. Did you receive the packet? When did you receive the packet? So it feels right, but you also get this benefit of being able to multiplex information through packets. You could get light frequencies, for example, and I think oscillations are a really big deal in brains, and the engineering folk are still working on taking advantage of that. What is my email address? jsn@ucsc.edu. Forgive me if I don't reply. I get 200 emails per day, but I'll do my best. Um, is it possible to have SNN-based analog printed electronics? Anything's possible if you set your mind to it. Yeah, no, I don't know what's been done in that space, so sorry. And forgive me for talking so fast. I'm trying to squeeze this all before I know we run out of time. Have I experimented with any alternatives to standard backprop learning models? Totally. Yeah, absolutely. None of this work really alluded to it. We've been very backprop centric on this. Why? Because it works, right? But I think that there is still a lot of value in looking at alternative learning rules. There was the phase of life where a lot of people were looking at STDP without global signals, but I don't think that that's enough. The forward learning rule, yeah, that you're right. Some of my students did put together a forward learning algorithm. So what's hot out right now? I think that real-time recurrent learning should make a comeback soon. I know Emre Nefci and a few other folk, I think Wolfgang Mass's group were working on RTRL for SNNs. That made a lot of sense. But then people moved away from real-time recurrent learning because cubic complexity with the number of neurons kind of superseded the benefit of removing time complexity. But the thing is that that only applies to dense recurrent neural nets with a full matrix dense recurrence. Spiking neural nets do not have a full dense recurrence. Like every neuron only talks to itself. It's got its own individual loop. So you get away from cubic complexity there. So RTRL makes a lot of sense. I think energy-based models are also super cool. It's effectively test time inference, and that's somewhere one of my students has been looking quite deep into. What's the state of the art understanding and hardware implementations of? Oh, okay, so amplitude, timing, firing rate, a combination, anything else. When it comes to large scale systems, I would personally just stay away from any sort of 1-0 mode of encoding. Why? Because it's such a small part of my total model. The moment I go into something small, unfortunately, the best we have is a rate code, I think, as far as backpropagation is concerned. But that isn't to say that the other codes are useless. I think it just means we haven't done the right job in figuring out how to make them useful. Let me keep going. What are some good problems that can be solved using neuromorphic computing? Hopefully anything that you just listened to me dribble about in the past hour. Is the described loop learning specific to SNNs? Totally not. I mean, the looped language model is applied to regular transformers, but we were just inspired by the recursive nature of loops from spiking neural nets, recurrent neural nets, and now that's kind of thought as a wrapper around a more, I guess, less neuromorphic piece of computation. So definitely not constrained. Yeah, sorry, I don't have too much insight with respect to power electronics. I can't know everything, unfortunately. How about EPROP? Totally. EPROP is a subset of real-time recurrent learning with some approximations made. And there's a ton of work out there on approximating real-time recurrent learning. Personally, I would just stick to RTRL and then fork off from that. Will edge computing be solely taken by neuromorphic computing? I personally don't think so. I mean, if I went to a regular deep learning researcher and asked them, hey man, I need this model run within this bound of performance at this within this power budget, they would start distilling that model. They wouldn't use a spiking neural net. They would go ahead with knowledge distillation and some sort of teacher forcing, I think. So again, it's really a case of use the right tool for the right job. Does your hardware take advantage of sparsity? If so, yeah, okay, then SNNs could make sense, or more generally, a sparse neural network could make sense. If your edge device is processing time static data, I stay away from SNNs or RNNs there. Then you just use a regular neural network that doesn't need to have any sort of recursion. Neural net model compression with SNNs. Yeah, I mean, totally. I think you just kind of foreshadowed what I was about to say with regard to distillation. Research visits at my lab. Yeah, shoot me an email. Neuromorphic is a buzzword right now. When is it possible that this becomes industry standard and reliable? I mean, I don't think it's just a buzzword. Otherwise, I probably wouldn't dedicate 10 years of my life researching it. It's already transferred into industry, right? State space models came from neuromorphic labs. Recursion came from neuromorphic labs. Sorry, recursion didn't come from neuromorphic labs, but applying recursion in that way started in Chris Elias-Smith's group in 2018. And now we're seeing a lot of language models that are recursive, that are very much based on the spiking neural net theory. So yeah, it's out there in an industry, whether you like it or not, I suppose. In terms of hardware, yeah, that's going to be a hard question, right? Overthrowing NVIDIA's moat is a challenge. Are there hardware or software neuromorphic standards or benchmarks? I think that Neurobench, led by Jason Yick at Harvard, is the right place to look for that. Do I wish to have my own startup focusing on low power algorithms and hardware? Yes. What is the idea about designing digital block of SNN, mainly LIF neural network? I'm sorry, I don't understand that question. I think I've addressed everything to the best of my ability on a time crunch. I guess that my resource constraint here wasn't energy, it was just time and latency. So yeah, if I wasn't able to address your question, I am sorry. I guess, yeah, feel free to shoot me an email or LinkedIn message. I will be on a 14-hour flight tomorrow, so feel free to entertain me during that time.
Okay, that's just kind of very hot discussions, and thanks, Jason, again. So
I don't think I've ever had that many questions in any talk. So yeah, thanks everyone for your questions.
Okay, thank you everyone. Again, thank you everyone for to attend our this month's the CSS webinar, and also appreciate Jason again to give this very wonderful talk and great answers to so many questions. Okay.
I appreciate you both. Thanks so much for hosting.
Okay, thank you everyone. Thank you, Jason. Bye.